Hi, I'm Viespoli and I'm a PhD student at the Norwegian University of Science and Technology. The work I'm about to present is the result of a fatigue investigation on lead alloy used for the production of sheathing for subsea power cables. The presentation will go through the motivation for such study, the cable architecture, the tensile and creep behavior of the lead alloy and its metallographic structure, its fatigue performance, and the crack surface investigation. Subsea power cables need a stable barrier to prevent electrical failure for water impregnation. Due to chemical stability and ductility, lead alloys are used for the production of the sheathing layer. The installation procedure, thermal cycling, and sea currents provide fatigue loads, while the technology and design according to which the cables are realized rely on long-standing experience, and most of the studies performed are several decades old. New research is being performed with the goal of a more conscious design due to environmental and economical considerations. Several cable geometries exist depending on the application. The specimens for this testing campaign were taken from a mass-impregnated high-voltage direct current type with an outer diameter of 82 mm and has a sheathing made of lead tin antimony, commercially known as E-alloy. The cable is composed of multiple layers. The innermost is the conductor itself, made of a bundle of wires of copper or aluminum. The insulation is in this case composed of kraft paper impregnated of pressurized oil, above which a 3 mm thick lead alloy sheathing is extruded. The lead is protected by a layer of polyethylene over which galvanized steel tape is winded to keep the internal part of the cable compacted. Two layers of almost longitudinal steel wires serve the purpose of bearing the cable's weight in installation, and the outermost layer is made of high-density polyethylene. The specimen for the tensile behavior characterization have been manufactured from the sheathing in a flat dog bone geometry. Due to the ductility of the material, digital image correlation has been used for all tests. The samples have been painted and the strain data extracted as the deformation average in the central part of the specimen. The tensile characterization was performed at room temperature in deformation control at different strain rates between 10 to the -2 and 10 to the -seconds, 1/seconds, and on specimens of different thicknesses from 1.1, 1.8 and 3.3 millimeters. Two main effects can be evidenced. The characteristic thickness of the sheathing influences the tensile response, with the 3.3 mm thick specimen reaching a consistently higher stress than the outer two. Given the low melting temperature of lead, around 320 degrees Celsius, creep deformation mechanisms are active at room temperature as well. This can be seen in a strong correlation between the deformation rate and the flow stress of the alloy. The metallographic structure of the alloy has been observed in the radial and tangential plane for all the three extrusion thicknesses. In all cases, the difference of grain size due to the cutting plane chosen is not significant, nor the grains look elongated in the extrusion direction. This should be due to the fact that room temperature is relatively high for lead, leading to recrystallization. The thickness of the specimen has a clear correlation to the grain size, with considerably bigger grains observed in the 3.3 mm of thickness sheathing compared to the grains observed in the 1.8 and 1.1 millimeters of thickness. The creep deformation mechanisms can be correlated to the steady state creep rate stress exponent. That is the exponent binding the applied stress and the deformation rate in secondary creep. This exponent, m in the formula, indicates diffusion-driven deformation up to a stress of 5 MPa and dislocation-driven creep deformation above 5 MPa for the material under study. The influence of creep on the tensile properties can be numerically described by calibrating a creep model in finite element method. In this slide we see the results of the calibration of the tensile results on a strain hardening power law creep model. This particular kind of model provides good results in the primary creep phase of the deformation. The specimens used for the fatigue testing were machined from 1.8 mm thick sheathing to different specifications than the tensile ones. In order to improve the resistance to buckling of the specimens and minimize the material deformation, the original curvature of the sheathing was preserved, that is, a radius of 82 mm. The fatigue tests were performed in displacement control in air at room temperature with a displacement ratio of -1 and 2 strain rates, 10 to the -2 and 10 to the -3 seconds to the -1. No other ratio, no other displacement ratio is really feasible with this material due to the extreme ductility. The correctness of the displacement range to reach the desired deformation range was checked at the start of every test with the digital image correlation. The stabilized cyclic curve can be obtained combining the points of nominal stress amplitude and deformation amplitude obtained in the central part of the specimen with the DIC for the tests at various deformation range and strain rate. Observing the results of the Ramber-Osgood approximation of the stabilized cyclic curve, the effect of strain rate is evident also in the case of fatigue testing. So this plot summarizes the fatigue testing results. A total of 9 specimens were tested at a strain rate of 10 to the -3 seconds to the -1 with 1 run out, while 13 specimens were tested at a strain rate of 10 to the -2 seconds to the -1 with 6 run-outs. The tests were performed in air at room temperature with the displacement ratio of -1. The clear result is an influence of the strain rate on the fatigue performance, influence which is correlated to the load level, yielding to a different slope for the two curves. In other words, for elevated deformation levels, the reduction of strain rate has limited negative effect on the fatigue life. The results diverge for lower deformation levels, at which the material results consistently stronger in terms of deformation versus number of cycles. It must be noted that if the difference between the results in terms of numbers of cycles is always inferior to 1 order of magnitude, meaning that the specimen subjected to the slower deformation will outlast the others in fatigue lifetime terms. The observation of the side cut of polished and etched fracture specimens shows interesting details of the fatigue fracture and how the strain rate and deformation level influences it. The upper series of pictures presents details of a sample broken at a strain range of 0.25% and a strain rate of 10 to the minus 2 seconds to the minus 1. The fracture appears to have propagated mostly in the plane orthogonal to the loading direction, and limited secondary cracking is present. The lower series of pictures represents instead the fracture of a specimen broken at lower strain rate and range. The two main differences observed are the propagation of the cracks, mostly along the grain boundaries, forming an angle of 45 degrees with the loading direction, and also branching, and a secondary cracking is observed, indicating how the material is damaged in several locations. A behavior this typical of interaction between fatigue and creep. The fatigue fractures of the same specimens on which the metallography was performed have been observed at the scanning electron microscope as well. In these images we observe the fracture pattern of a specimen broken at a strain range of 0.25% and a strain rate of 10 to the minus 2 seconds to the minus 1. The fracture is mostly transgranular, with some secondary cracking and grain decohesion, indicated by the arrows. In these images we can instead see the SEM imaging of the fracture pattern of a specimen broken at a strain range of 0.15% and a strain rate of 10 to the minus 3 seconds to the minus 1. The line in the figure indicates the boundary between a region in which a fracture is characterized by a mix of intergranular and transgranular propagation, as seen in figure P, and the region of the external surface in which the fracture is totally intergranular, as seen in figure C. Figure D shows the external surface of the sheathing with the grooves left by the extrusion process. A secondary crack is visible on this surface. The main conclusions of this series of fatigue testing on commercial lead E-alloy is that the strain rate affects the fatigue behavior even at room temperature, influencing both the cycles to failure and the failure mode, with a slower deformation introducing more creep damage and causing an increase of grain decohesion. A natural future development in the scope of the project is to combine the experimental data for the implementation of a fatigue model for the prediction of the actual life of the sheathing. This is a challenging task since the cables operate at strain rates much inferior to what is experimentally feasible to test, leading to the necessity to extrapolate these results. Thank you for your attention.